For our next speaker, I am delighted to introduce Dr. Andrew Chien. Dr. Chien is the William Eckhart Distinguished Service Professor of Computer Science here at University of Chicago. Dr. Chien holds a PhD in computer science from MIT. He is a leading researcher in topics of cloud software and hardware, supercomputer architecture, and sustainable computing. He leads the large-scale sustainable systems research group here on campus. He's a fellow of the ACM, IEEE, the AAAS, and he currently serves on the National Science Foundation's CISE Advisory Committee, as well as DARPA's Information Science and Technology Study Group. He's published extensively on carbon emissions of data centers and opportunities for use of renewable energy in computing. We've invited him today to speak on issues of AI and machine learning and sustainability. So I'd like everyone to welcome Dr. Chien.
Thank you very much for that kind invitation, and it's great to be here. I thought I would start by introducing myself, but David already did such a nice job, I don't have to say too much. What I would like to say is that I came into this in a funny way. So I spent probably 20 years of my life as a card-carrying, computer system building, high-performance computing researcher, trying to build more and more of computing and make it more and more powerful, and bring all of the wonderful things that we know computing actually can bring. After 15 years as an academic, I spent 5 years as a VP of research at Intel, driving all kinds of advanced technology. And when I left there and came to U Chicago, which was a wonderful transition, I realized actually that we were looking at the end of Moore's Law. So this was about 2011. Being a professorial type, that's what I discovered about myself when I was at Intel. I started to think, what does that mean? What does that mean for the future? And my work in sustainability and large-scale data center environmental impact is a direct consequence of the realization that technology scaling was coming to an end, or coming to a slowing, and what the consequences of a world that had an insatiable desire for computing, connecting with a world in which the technology progress had been is slowing, what was going to be the result of that. So you'll hear a little bit of that story. Okay. So just to give you a little bit sense of who I am, here at Chicago, I'm currently teaching 2 classes. So these are sort of the 2 sides of my research head. One is I'm teaching a class on sustainability in computing, which is an attempt across the university as part of the Big Problems curriculum. So it's cross-listed with environmental science, and it's cross-listed with SIGU, which I always struggle at the acronym for SIGU, but those of you who are from Chicago know that. But it's geography and urbanization and complex, social structure dynamics. And that class is really trying to bring technologists and public policy and economists together to think about these problems in a sophisticated way. And then the other side of my head, we're working very much on advanced computer systems architecture. I still do that kind of stuff. Okay, so that's about me. Let me kind of dive in. What we've done over the last 10 years, so I started working in this area about 10 years ago. We started a project called Zero Carbon Cloud, which was trying to figure out how you could compute in a data center in a way that had no carbon emissions, right? Well, at least no operational carbon emissions. And the idea we came up with was to exploit excess renewable energy, or stranded power, which was an outcome of the fact that when we had renewable energy, it meant we could no longer control when generation happened. Right? Sun shines, generation happens. Wind blows, generation happens. Sun goes down, wind stops blowing, generation doesn't happen. So the idea here was to actually take data centers, which traditionally live on the reliable side of the power grid, and move some of them to the unreliable side of the power grid, where all of this fluctuating generation was happening. And this crazy idea to exploit excess renewable power, that is generation that was happening when there was no corresponding load, turned out to be actually kind of a useful idea. And this allowed you to exploit free power or nearly incrementally zero carbon power. And this has become a reality for some of these large AI and Bitcoin facilities in Texas. And it actually spawned a company that I helped launch, but I'm not a principal in, called Lancium. And so this was the most wonderful thing that could happen to a professor. You work on something a long time ago, and then somebody picks it up and it becomes some big commercial activity, right? So that's how we got this start, with this radical idea that all the big data center companies said, I don't want that data center, it's unreliable, right? But here's this way, right? Show the way, right? That's what academics are supposed to do, to make a data center operationally near zero carbon, right? And it turns out, actually, you can almost do this for up to 90% availability in Texas today. So it's not like it's off half the time. It's off like 10% of the time. Okay, so that's a little commercial about sort of what I've done as backdrop. I'm going to try and cover all of these points, but let me just sort of jump in. So we all know, right, cloud computing has been a huge and growing impact on the power grid. So this is a projection from a report in 2020, where the headline report actually got it wrong. But if you look at the data, you could figure out that the hyperscale companies like Google, Amazon, Microsoft, and so on, actually had a power profile that was growing exponentially like this. So this was projected about around 2020, right? So all of these were projected data. So it was already bad. It was 30% compound annual growth rate at that point. So if you looked at the data in the right way, you could see this. And we had a huge falling out with the data scientists who wrote this report because they have a different diagnosis, right? Fortunately, from my point of view, it turned out that our diagnosis was right. Their diagnosis was very conservative and not. But actually, both of us were wrong, because that was the projection for hyperscale. But what happened is this. What happened is generative AI showed up, right, and blew the top off of all of these projections. So it sort of didn't matter, who had gotten it right. But the point is, this fundamental trend is coming independent of whether AI happens, independent of whether the bloom goes off of AI and so on. We're seeing this gigantic growth in computing power requirements. Okay, what does that actually look like? Now it's easy to find lots of, when it goes from the technical projection to the business projection, it's serious because the money's flowing as a consequence of this, and that means it's likely to actually happen. So, early last year, outfits like Goldman Sachs and all of the other, big business projection folks started saying we were going to see dramatic power growth, right? This is the data center power use in terawatt hours. The units don't matter so much. The trend is really what matters. But the center line gets us to, I think, 8 gigawatts incremental increase. 80 gigawatts incremental increase. The low scenario is 40 gigawatts, and the high scenario is 120 gigawatts by the end of the decade. So super large increases, right? One good question to ask is, there's just people running around saying there's a big crisis for power generation in the US, and how are we going to solve this crisis? So an interesting question to ask is, how exceptional is this demand? Right? Is this really such an unusual thing? And if you look at the place where power generation has been growing the fastest in the world for the last several decades, it's actually China, right? Not a surprise if I tell you this, but the magnitudes might surprise you. So China's power grid has been growing about 8% CAGR, so significantly faster than would be required for the US to meet this power growth requirement for data centers for the last 25 years, something like that, right? Well documented. And if you look at this chart, the size of the Chinese power grid surpassed that of the US power grid about 2010, so about 15 years ago. And it's much larger now, right? So you can look at this graph and say, okay, it's at least 2 times larger, right, than the US power grid. And they're still growing at 8% per year, right, more or less, right? So really, it's not that exceptional that you would have this kind of power grid growth. What's the big challenge in the US now is, and maybe in Europe as well, is how do you deal with the public policy aspects, the regulatory aspects, and the societal impact aspects of this kind of rapid growth, right? From a technologist's point of view, it's like, okay, we can invent better ways to do it, but we know how to do this. We know how to build out this kind of a grid. It's not a technological problem. And by the way, even so, I don't really mean to question that this AI boom is happening, but we also know that large-scale electrification is going to happen in other dimensions, whether it be electric cars, electric heating, other kinds of things, right, where we want to convert, fossil fuel use into electric power use. Yeah?
Thank you. May I ask a naive question? What's the difference between cloud and data center?
Cloud and data center. So actually, let's talk about 3 things. Let's talk about cloud and data center and AI, right? because that's often what people ask. So the data centers are the physical constructs, the buildings, right, that house the computers that are used to do all of this computing. When we talk about cloud computing, we mean the practice of taking computing that was traditionally on premises, like in a data center here at the University of Chicago, and being shipped off to some data center that Google runs or Microsoft runs or Amazon runs. So we would call that cloud computing. That cloud computing traditionally was like IT services, like ERP, employee records, your payroll, that kind of stuff. But now increasingly, right, it's AI, right? So cloud, it is kind of confusing, right, to call it cloud and data center and AI. But that shift to these hyperscaler data centers is usually what we call cloud, and these physical data centers, which could be serving either traditional IT applications or AI applications, or increasingly it's difficult to tell the difference between the two because AI is getting put inside of all of these applications, right? It's all AI computing or it's all traditional computing, depending on how you want to label it, all runs in what we call data centers, right? And the other interesting, it's a great question, and the other interesting thing to realize is that, back when I worked at Intel 15 years ago, most of the computers that were sold to individual companies to put in their enterprise IT data centers, or to individuals or companies for laptops and now then smartphones after that. But now increasingly on the server side, I think more than half of the servers now and AI equipment, of course, are being sold to these very, very large cloud companies. It's not the small Fortune 500 companies buying these things. It's the computing specialized companies that are buying these things. Great question. I'm happy to take questions. I'm going to have to adjust my number of slides a little bit to accommodate that, but that's good. But the other thing is that China gets a lot of grief for you're growing that, and your growing power grid is going to destroy the climate. But it's actually really not a fair characterization. So what's not often realized is that a lot of the growth in China is renewable generation. They're the world's largest builder of renewable generation. They have the world's fastest growing. They're the largest producer of renewable energy and all of those kinds of things. And there's some evidence that in the next few years, they're going to peak in terms of carbon emissions. And no small part of that is the fact that their grid is being rapidly. So it's not an either or thing. You can grow and still decarbonize is the point, right? Okay. So what's happening in the US is a little bit difficult. The utilities are struggling to keep up, right? So this is a sequence of forecasts from the power utility for Data Center Alley, right, in Northern Virginia. You may hear about this, Loudoun County, or now there's another county. They were too big. They actually are spilling over into the neighboring county. I think it's called Ashburn. And they're required every year to do a 10-year forecast, okay? Tough to do a 10-year forecast in this business. But this is their 2020, 2021, 2022, and 2023 forecasts. And you can see they're trying to keep up, right, with these rapid upward revisions, right? And what I heard on the radio yesterday, was that 45% of the power revenue, right, in this power grid was from data centers last summer. And it's about 35% of the load today. And what does that mean? Well, if you're 35% of the load, it means you can't double much anymore, right? You've been doubling for all these years. How many more doublings can you do when you're 35%? Well, of course, it's not a zero-sum game. The total can grow, but just a couple of more times and you're dominating everything is the point. Okay, so we don't know what the next upgrade is going to be, but it looks like there's going to be another upgrade. Now, what's happening for this, and why should we be worried about carbon emissions and climate change? Well, what's happening is that we're seeing high and high peak forecasts, and the peak forecasts actually determine what generation gets put in place, right? So because they have to have enough generation to meet the peak load so that the grid doesn't go down. Nobody wants the grid to go down, right? To crash, blackout, right? So there's a gap of like 14 gigawatts, and the question is, what should the utility do about it in order to meet this gap? And if you look at the plan, so in addition to the 10-year forecast, they have to produce a publicly vetted plan for how they're going to meet this forecast. So this is a virtue of all this public utility transparency and so on. I think it's great. But the challenge is, if you look at what they're forecasting, they're actually planning to build 3 gigawatts of natural gas. Oh, wait, we had to revise up. We're building 6 gigawatts of natural gas, right? So it's not that great that they're building more fossil fuel generation to meet this need. They're also taking on renewables. But they're building lots of fossil fuel generation to meet this needs, which means they may not be able to drive their carbon down, right? But the bigger problem is they're building an infrastructure that by law is supposed to operate profitably for 30 years, right? Which means you can't kick them off, you can't turn it off, right? Because there's a contract, right? A business contract in place that you get to, earn enough revenue to pay off your capital expenditures. That's the fundamental economic model that's being used for these public utilities, right? So the people who are really concerned about us are worried that we're creating a 30-year foundation in fossil fuels as a result of this growth, right? So we won't be able to fix that anytime before, what's 30 years from now? 2055? It's a long ways away, right? Okay, so that's one dimension, right? Growing power use, right? Second dimension, it turns out data centers use lots of water. What the heck does a data center use water for? I don't have to put water into my laptop. What are you talking about, right? Well, it turns out that data centers have a bunch of parts, right? Here's a picture of a data center. I also do research on data centers. And the power comes in over here, where it is shown as red. Here's where the computing equipment is over here in blue. Here's a bunch of power conversion stuff and reliable energy. But the problem is all that heat comes in, all that power comes in, and the computers basically turn it into heat, right? They turn it into this disorganized energy, right, that we know as heat. And you got to somehow get that heat out of the building. Okay, 10 kilowatts, you can kind of imagine how much heat that is. That's like 8 or 10 microwaves running, generating heat. That's a decent amount of heat. But now I tell you 100 megawatts, or I tell you a gigawatt, like people are talking about a gigawatt, right? That's a gigantic amount of heat, right? Anyone seen a nuclear power plant? Sure, you've seen a nuclear power plant. At least you've seen a picture of a nuclear power plant. It's got this big cooling tower thing, right? That cooling tower is used to get the gigawatt or so of heat out of the nuclear power plant, right? And that's the waste heat that couldn't be used to generate electricity. So you should be thinking there has to be some big physical apparatus, right, that's actually getting this heat out. So that's over here. In these data centers, we have chillers, like air conditioning units, and then we have these cooling units, which sit outside, and they're big fans, right, blowing air over these hot water pipes, right, that's actually getting rid of the heat. Now, it turns out that people discovered that you can do this really efficiently by using what we call Texas air conditioning or something like that, where you spray water on it and the water evaporates and that phase transition carries away heat, right? It absorbs heat, right? We all know this. We've all done this on a super hot day, maybe when our air conditioning wasn't working, right? So that's what they do in data centers at scale. They spray this water in the air and they use it to take away the heat, right? And that's how they consume water. And they consume voracious amounts of water, right? So now this has become a serious consideration for environmental impact. Now, to give you a sense of how large the water is, right, there's some brilliant professors at UC Riverside that did studies that show that something like 10 to 30 milliliters of water are consumed per ChatGPT conversation. So, 10 to 15 prompts, maybe your favorite undergrad's just messing around, right? Okay, 30 milliliters of water. Okay, another 30 milliliters of water. How much water could one undergrad consume in one night? I'll leave that as an exercise to the audience, okay? Now, I do research on data centers, and it turns out technically dry cooling is feasible, right? So you can do all of this stuff without evaporating water, right? So you don't have to consume water, but consumes more power, right? And it may be more expensive, right, to both consume that power and to build the facilities to do it. So there's this continuous trade-off. You can choose to operate dry, you can choose to operate wet, and it affects things like energy overhead, it affects things like total cost, it affects things like carbon overhead, right? Because if you consume more energy, maybe you're causing more carbon emissions and so on. So it's a complicated trade-off, but it's technically possible. And now there's a big push to try and reduce, right, water use, particularly in areas where data centers are in water-stressed regions, right? Like if you're building data centers in the southwestern United States, using water in this way is really not a very good idea, right? And now in Texas, they're worried about droughts combining with these kinds of data center problems, and so on and so forth. So what is actually going on in this space? Microsoft, one of the largest hyperscalers, had a history of water use growth of like 22% a year from these very, very large numbers. These are millions of cubic meters, right? So this is 7.8 million cubic meters in FY23. They've set the goal, right? So now they've gone from carbon goals to water goals, right? And they've set the goals of being water positive by 2030. I never heard the term water positive before, but it appears in the sustainability business, inventing new terms is a direct technique for trying to assuage these concerns. It's not necessarily a technique for really solving the problems, right? It could be, right? That's not necessarily. But I would be hugely skeptical anytime somebody invents a new term and you say, well, I don't even know what that means. That's right, because probably they're controlling the definition for their own ends, right? Yeah, another question.
Thank you. How about OpenAI?
How about OpenAI? Are they consuming water? Yes. They definitely need more water, yeah. I try not to pick too much on individual companies. I will talk a little bit about OpenAI and some of what they're doing later. Okay, so now there's a huge debate amongst these folks. Who's going to be water positive? Who's going to stop using evaporative cooling? Who is and who isn't? Microsoft has actually announced they're going to have all their new data centers not do evaporative cooling, but we're not going to fix the old ones. It's too expensive. Okay? I don't know, maybe defensible from a business point of view, but not fully satisfying, right? Google has said, I don't think you should hold us to any absolute standard like that. You just trust us to do the right thing in the right places. So in places where there's water stress, we're not going to do it, or we'll do it less. And places where it isn't, you should let us use water because that's what's better for the environment, right? Because it does reduce energy, right? So it's a complicated kind of discussion. But this is another criteria about this. And you'll see things in the news about individuals, right, worried about their water table, water prices changing in addition to energy prices changing, and so on. And then there is the big concern about just withdrawing water from the ecosystem and the impact on biodiversity. Microsoft is putting a big data center up in Wisconsin, just north of the border here. You may remember there was a promise to build a large Foxconn plant there. Right? When the Foxconn plant was proposed, they had to make an ask for water use, right? Because most industry, most actual physical industry consumes water. It's not like only data centers, but data centers consume a lot. And there was a huge hubbub about, we're in the biggest freshwater rich part of the world, I think, right? The Great Lakes region, right? We have more fresh water than anybody, not just in the US, probably globally, right? But nonetheless, there's a huge concern about, whether that's appropriate use of that water. So if we've got a problem here, can you imagine what it's like in Arizona, right? Can you imagine what it's like in West Texas? Can you imagine what it's like? So this is a serious problem. Okay. So what are some of the problems? Well, I already got into this. So the growth of these data centers causes problems with power use, and that affects the grid. It makes it likely that the grid is slower to decarbonize. That was our dream for decades, right? Or maybe worse, it could be recarbonizing the grid, right? If much of the load, you asked about OpenAI. Let's talk about xAI for a minute, right? So that's Elon Musk's company that builds Grok, the chatbot. They put in a data center in East Tennessee, and in order to power that data center, because the data center is 2 times bigger than the local power utility, okay, that gives you a sense of scale, they actually put up a bunch of natural gas generators across the border. I think it's in Mississippi. I don't know if I have my geography right. And they could do that because they could get permits in Mississippi, and they had influence and pull, I guess, with the political system there. And then they are running the power across the border into Tennessee to consume it, right? So a couple things are not great. First is all that power is fossil fuel generated, right? I don't think any of it's renewable, so that's not so great. Second, they're going around all of the procedures and policies we have to protect the environment, right? So that's an example of sort of an extreme challenge. Okay, so now we have competition. We have rising power prices for everybody. We're just starting to see that, but we're likely to see that accelerating over the next couple of years as the stress in the power grid continues. And now, things are so serious that people are seriously talking about and putting billions of dollars behind nuclear power. Right? Now, I'm not going to weigh in on whether I think nuclear power is a good idea or not. I'll let you, resolve that. But it certainly is mostly carbon-free, right, in terms of carbon emissions. But it has huge other external risks, of course, right? But I look at it very practically, and I say all of that power production for nuclear power is 2030 and beyond, right? Read the press releases carefully. It's 2030 and beyond, and it's very small in 2030. And data center use is going to be this big in 2030, and it's going to be this big. So my practical reaction to that is, okay, you can talk about nuclear power, but don't pretend like it's actually solving the problem. The problem is going to be addressed some other way, right? It's a distraction. It's a ruse. Okay, second, water use. We just talked about evaporative cooling, water table concerns, biodiversity loss, all of the things I think that are front and center for everybody. And then there's life cycle impacts of IT compute and network electronics. What do you do with the electronics? How long do GPUs last? How fast do you have to churn these things out? And what do you do with them? Power electronics and cooling equipment, right? That picture I showed you of the data center, well, the IT part was just like a part of it, right? There were like 4 or 5 other large complexes. They're large, right? And then there's actually this problem with data center buildings. As AI requires more and more dense computing, it turns out that the buildings were sized for a particular density of power, right? Like maybe 25 kilowatts per rack. These numbers may not mean much to you, but let me just dial up the contrast. A standard cloud computing rack of servers was maybe 25 to 30 kilowatts per rack, in the pre-AI era. And these dense AI complexes for AI training are 150 kilowatts per rack today. So 3 to 4 times more dense, and the next generation is 600 kilowatts, right? So you're seeing what happens to these data center buildings is you come into a room like this and all the IT equipment is in 3 little racks in the corner and the rest is empty, right? So this is a problem for real estate. This is a problem for people who pay for physical infrastructure and so on and so forth. Okay, how am I doing on time here? I'm going to have to do some quick surgery here. I was going to talk a little bit about why deep learning is causing power use to grow so fast. Is that a helpful thing to talk about? People want to hear about this? Okay. So deep learning is a subset of machine learning, which is a subset of AI. So it's by no means all of AI. And I always have to say that for my computer science colleagues. But the fundamental idea is that deep learning is useful and powerful because it allows us to learn a task directly from raw data, right, meaning all of the text on the internet, without a lot of human intervention. Okay, there's a lot of human intervention, but it's not content human intervention, right? It's process human intervention. And this is super powerful because the big limiting factor for AI before was something called feature engineering, where you had to basically define the subject and tell the learning how to focus itself. Deep learning is largely unfocused learning that focuses itself, okay? So fundamentally, why is it expensive? Well, it turns out that the fundamental building block is something called a perceptron or a neuron, right? Which computes on a bunch of weights. You probably heard these terms. Weights, takes these inputs, multiplies them by the weights, adds them all together, applies a nonlinear function, and then produces an output. Sort of an approximation of what happens in all those neurons in your brain, except much, much simpler, right? People build layers of these. So think millions of these neurons in a row, and then hundreds of layers of these neurons, right? So you go from one neuron to billions, it turns out, right? Billions, okay? So the way that we size these networks is we typically talk about how many weights they have, right? So a common model like llama, right? You might see a 70 billion llama model, right? ChatGPT, well, we have to say which number. ChatGPT 4, I think, was like 800 billion weights. So the reason they're big is there's lots and lots of these neurons being used, right? That's basically the scaling problem. So every connection, right, every one of those little lines is a multiply and add operation, typically in low precision floating point. These operations are amongst the most expensive operations inside of a computer, right? So that's one of the problems. Each inference activates as many as all of those connections if we had a simple model. But if I have some kind of transformer or BERT model, I don't know if you know those kinds of terms, they do something called focused attention, which is they only turn on some part of the neural network. So maybe you could get down to 10 or 15% of that, but it's still a big number. And then the computation fundamentally grows with model size. So if you have nobody knows how to reason about, or few people know how to reason about actually how long something takes on a GPU, but we all use laptops. We all know what things kind of take on a CPU. So if I have millions of weights, it takes something like milliseconds to run on a CPU. If I have billions of weights, it takes like seconds to run on a CPU. And if I have trillions of weights, maybe it's running like 20 minutes on a CPU, right? And the biggest models, oops, my slide got messed up. The biggest models are about 1 trillion weights today, right? So these are not crazy numbers, right? So that's for one inference, one use of the model from input to output. So that's why that's getting big. Now, there's these nice dashboards you can find. So Hugging Face actually has an energy consumption dashboard And this is the benchmark they run for text generation, chatbot, right? Or program generation or something like that. The typical mainstream use you hear about for AI these days. These numbers for a 70 billion weight llama model are 1,648, this makes me crack up, 0.51 watt hours. Why the heck are they reporting 2 decimal places? It's scientific distraction, right? Okay, so, but what the heck is a watt hour? We're not used to thinking about watt hours. And this benchmark is 369,000 tokens, which is inferences, right? Each token is one inference. And this 70 billion weight model is 10 to 15 times smaller than the largest model, right? So just for calibration here. So this is something like a large model would be 16,000 to 24,000 watt hours for this, which gets you to about 0.05 watt hours per token, right? So how much power is this, right? So this comes to OpenAI, right? If you want to try to use this to estimate, OpenAI will tell you we've got 2.5 billion prompts per day that we're serving, okay? That's their global market, right? And each prompt produces something like a 200-word response, right? Maybe that's a little long, I don't know, it depends on what you ask it, right? And it turns out they're running the model multiple times underneath. They're sampling different responses, and they're giving you what they think is the best of those responses. And sometimes in some chatbots, you can actually ask it, I didn't like that response, give me your other response, right? So you know this is going on statistically. So this, if you do the computation, this gets you to 100 billion watt hours a day. How much is that? That's about 100 gigawatt hours a day, or on a yearly basis, that's about 25 gigawatts sustained, because it's 24 hours a day, right? And so how much power is that? Well, if you normalize in terms of US homes, right, a typical US home, if you ask the EIA, it's about 30 kilowatt hours a day, right, depending on where you live. So it's about 3.3 million homes, right, is equivalent of just what ChatGPT is running. Now there's other companies, right? It's not just ChatGPT, right? And then, you know, if you compare it to EU homes, right, I'm always embarrassed by this number. Their daily consumption is much less, right? So like, amazingly less, 6 times less. But you have to keep in mind, their houses are about half as big. So I'm not completely unhappy about that trade. Right? Okay, so that's the kind of problem that we're facing, right, in terms of power, right? And you know, you shouldn't think ChatGPT is the only one out there. There's lots of organizations training foundation models. I'm not going to talk about training, but training is a significant portion, but inference serving is the largest. And now people are talking about sovereign AI, which means other parties are going to train these things just for, what's it for? Sovereignty, pride, non-economic considerations. I have no idea how you control that, right? Right? That's like a AI proliferation problem or something like that, right? Okay, so the point is this is likely to grow, right? Okay, okay. So the big LLMs get all the glory. These are just the biggest LLMs. There are small language models, and there are other kind of deep learning models and so on and so forth, and one should not ignore those from a use and application point of view, because if you can use a smaller model, you probably should, right? If you can use a smaller model and get adequate performance or equal performance or something like that, you really should. And what we see right now is a big rush to use the biggest models, because it's like a trophy to be using the biggest models. I'm using the best, right? We don't know if it's the best, but it's probably the highest capability, right? But smaller models often have equal performance or can even outperform in narrower domains, right? So don't think that the biggest is necessarily always the best, right? But in this chaos and turmoil, right, that we're in right now of rapid change, it's often the easiest recourse to just grab the biggest things, right? And then there's new applications and data types. There's so-called reasoning models, which actually do multiple inferences, many inferences underneath. There's something called agentics, where they're going to have the computers talk to each other. Right. So who thinks the internet actually is primarily people talking to computers or people talking to people? No. It's mostly computers talking to computers, right? So this stuff, agentic stuff, is likely to be even bigger, right, than any of the things we're talking about, because humans can't interact fast enough with AI, right, to really drive such huge growth. Computers interacting with each other can do it really fast and really drive, you know, sort of exponential growth, right? So we've just begun to see what's coming. And then, of course, just yesterday, Sora 2 was released. Anyone hear about Sora 2? Yeah, okay, so good. People are paying attention. So Sora 2 is this image and video generation tool that was put out by OpenAI, right? And so you might ask, oh yeah, what is the internet filled with? It's actually not filled with email messages, right? Most of the internet is video. From a streaming point of view, as in total traffic, from a total content and data storage point of view, it's all video. Why? Because I can sit and consume gigabytes of video in just, 30 minutes or something like that. How long would it take me to consume gigabytes of text? Maybe the rest of my life, right? I mean, so there's a scale difference, right? So video is just coming, right, in scale. And people have been doing experiments for a while. But there's reports that try and calibrate how much more expensive AI could be for video. This report, creating a 5-second AI video, is kind of like a way to characterize this. So if a microwave is 1,200 watts and an hour is 3,600 seconds, then that's 4.3 megajoules. That's what my engineering head likes to use these units as. But let's use these watt-hour units that I used just a minute ago. It's 30 times the text prompt example, right? So from the text prompt to a 5-second video, 30 times. And then, of course, do you think they're going to stop at 5-second videos? No, of course not. TikTok formats are way longer than 5 seconds now. I think they go up to 3 minutes or something. But, maybe most of them are 30 seconds or whatever the attention span of a, dare I say, 40-year-old? Or a 15-year-old. I'm not sure who the market audience is. But there's evidence right now that the current techniques have superlinear growth, right, in the length of the video. It's not linear, so 30 seconds is not 6 times more. It might be 20 times more, right? In fact, the data produced was quadratic, right? But I think it'll get better, right? It's probably not going to be quadratic forever, right? But it's likely to be superlinear because when you generate a video, there are some constraints that extend across the time horizon, right? There's a plot. These things are supposed to be connected. The behavior is supposed to be connected, right? So there has to be some things that scale across. But we'll see. Either way, I think it's a lot larger. Right? Okay. Oh, okay. There's my SORA 2 thing. All right. So what can we do about it? Well, here's a couple of things we can do about it. I'm going to try and finish in, let's see. Let me try and finish in 10 minutes so we can do some questions. So one of the things you can do about it is use less, of course. But one of the big things you can do about it is try and exploit variability in the power grid. And that's useful from carbon and cost point of view. So if you're to provision a service for your university or for your library, this is one of the things I think you should think about. So it turns out, quite surprisingly, I think to many people, that there's a lot of geographic variability in carbon, right? So this is a plot from, what happened to my little label? Okay, I meant to give credit. There's an outfit called Electricity Maps that plots real-time carbon data for most of the world now. Pretty astonishingly, they actually have power data for China in real time. I don't know how they get it, but Europe, US, South America, and so on. And this plots the carbon intensity, and this, you can see like when renewable generation comes online and when the sun goes down, and it affects all these values, right? So the point is there's a lot of geographic variability, and we did some work a couple years ago pointing out that if people just took and transshipped their equipment to data centers that were in lower carbon areas, right, for things they don't care about being far away, right, then in fact, they could dramatically reduce the carbon footprint of their computing, right? So you might ask, oh, I can't ship it that far away. My students want to use it here, or my researchers want to use it here. Well, it turns out for most use of computing, right, especially these kinds of analytic uses, you don't actually need like a 1 millisecond response time. You're not controlling heart surgery, right? You're asking and then you're waiting back. So next time you use a generative AI tool, try and sort of figure out how long it takes that response to come back. 50 milliseconds, 100 milliseconds, seconds sometimes, right? Typical use, right? So it turns out with modern networking technology, if you have that kind of delay, you can put it anywhere in the US, right? And we did a study which showed you could do load balancing over the whole world, right? And you could dramatically reduce carbon emissions. So this is a serious consideration. Probably, if you're not personally building data centers, you're not thinking about where to put a data center, but this translates into which provider do you select and where do they locate the computing and so on. That can have a big impact on carbon use, right? This is the simplest way to do it. And the simplest way to do it in a way that's not misleading or complicated or fraudulent is to look at our average carbon intensity for the power grids where the data centers are, right? Just average over long periods of time, like last year, right? Because that's the hardest thing to cheat at, right? Okay. The second level thing that you can do, right, is that these power grids all have fluctuating generation. So this is the amazing fluctuating generation that happens every day in the California power grid. This big yellow splotch in the middle is solar generation, which comes every day, right? These are 4 days of the week. And the amazing thing is it comes every day, and now it dwarfs the rest of generation. This is like the worst dynamic problem you can imagine. I guess this is probably like, students showing up in a library. They all come during certain hours, and then they're gone the rest of the time, right? Okay, but this balancing act happens every day, and what this means is if you consume power during this period, you could argue it's practically carbon-free, right? But even in California, if you consume power in this period, meaning at night, no, they're running natural gas plants, actually, to provide that power, right? So in addition to the geographic choice for where you put this stuff, there's actually a benefit in using power at the right times, right? And I'll get to that with some recommendations for how to use AI a little bit later. Okay, so the basic idea here is you'd like to align your use with low carbon power. And fortunately, because renewable generation tends to be cheaper than fossil fuel generation today, it also aligns your use with low price power, which means hopefully you can get these services for cheaper, right? If you can do this. Okay. This problem is getting more extreme as you add more and more renewable generation, and these are the RPS goals, the renewable generation goals for a number of states and European countries and so on. And these goals all go up into the right very, very fast, as you know. The timescales here are long, right? These are 2030, 2040, and so on. But there's no question where we're going kind of long term, right? Okay, let me just skip this. Kind of talked about this already. Okay, so one of the things that we've been trying to challenge the industry to think about and get them to think about computing is for about 5 years we've been telling them there's good, better, best, because we don't like to offend people, right? So you're not evil people, but you're only doing good now, and you could do better, right? So it's the positive way of saying it. So what happened is that, and Google went through like this 3-stage cycle, right? So these companies used to say, I'm just going to offset my use. I'm going to buy carbon offsets, and I'm going to make myself, carbon neutral. Turns out offsets are largely a fraud, right? If you've been reading the papers, they've been scientifically debunked. 2/3 of the offsets transacted in 2023 were effectively proven scientifically to be fraudulent, right? So it's very, very hard to make offsets not fraudulent. But the problem is basically you have this renewable generation as shown on the left here, and then you have data center use, which looks something like this flat on the right, right? So we've been advocating that you should do better, and Google and Microsoft actually adopted these goals, and their idea was to do 24/7 matching. So instead of just saying we bought all this renewable power, we used all this power, and they wash, right? Doesn't matter where they are, doesn't matter when it happened, right? That's literally they were buying contracts on some continents that were different from their data centers and claiming it's sort of all washed out. That's crazy. No way that could actually happen, right? But it's an accounting method, right? So they don't care, right? Okay, so then they said, okay, we're going to do better. We're going to have 24/7 matching. We're going to say we're only going to offset our carbon use if at the time we're using the power in that local power grid we have a contract to a renewable generator and it's generating. Okay, so this is much better. So this is like, the idea is that, we have this green use and then we want to get more and more renewable energy, and then eventually it will cover all of the brown, which is the data center use, right? And their goals were by 2030. Basically, they've announced they're not going to make it, right? They're going backwards, right? And they're about to recant their goals. I predict in the next 18 months, you'll see these major hyperscalers recant their climate goals. They'll say, I'm sorry, AI is too important. We can't make it, right? That's what they're going to say. Okay, but we're pushing them to be best, right? And so what we'd like to see is that you have the loads be somewhat flexible. And that means that you flex up when there's excess renewable generation. That was our zero carbon cloud idea. And then you create a floor for green energy using energy storage or additional transmission or other kinds of things, and then you make your load compatible with this. So this is the only way to get to a 100% renewable grid, is you have to have some load flexibility and then some additional costs associated with making renewables available on demand when we want to use power, because none of us wants to do the cartoon thing like, oh, I can't turn on my dishwasher now, I have to wait until the sun comes up, right? We don't actually want to quite think that way, though we might want to adapt our behaviors a little bit, right? Okay. So, okay, I won't get into all the greenwashing that's going on But I will say you can't quite believe what the data center companies tell you. We did a study of Google's own, right, sustainability report using their data, and we were able to show that because they're using this not so accurate market-based accounting technique, which is, by the way, accepted widespread corporate practice, they're underestimating their actual emissions by about 2/3. Basically, we did the study, and we were able to figure out that all of the work they did, picking good places for data centers, engineering the heck out of them, and so on, they wound up having emissions that were 95% of doing nothing, right? So not making a huge impact. And they're claiming they're having a huge impact when they're not having a huge impact. So the short story here is you have to look at all of the claims from the vendors with a grain of salt, because they're using self-defined, self-supporting kinds of metrics. There's no good government regulation about this in the US today. The EU has some regulations for rules about how to report these kinds of things. And if you can get people to report to those rules, it's probably okay to use their data. But I wouldn't trust any of the self-reported stuff in the US these days. Okay. And I'm not picking on Google. Google's probably one of the better actors. I always say this as a caveat. The only reason we can analyze their stuff is they put out enough data that we can actually analyze it. So I'm not criticizing them as an individual corporation, but they're an exemplar of probably better than average practice across the industry, right? Okay, I'm going to run out of time, and I want to have some questions, so let me get to the advice. Oh, okay, I'm almost there anyway. So, what to do? Trying to be helpful here. You guys seeing that? Okay, so what to do? So here's some strategies for reduced environmental damage and growing AI ML use. Don't use it. I don't think that's going to happen, right? Don't use it, right? Or use as little as possible. That's a semi-serious kind of thing. This is like don't waste, right? Don't create structures that encourage yourselves or students or researchers to waste, right? And that's things like free unlimited use, right? That's things like unlimited access over the internet from whatever site you can come in. You guys know what all these things are, right? And the tension is, I'm sure all your organizations have some incentive to show how you're enabling use, right? But you want to enable real use, valuable use, not just frivolous use, right? And I had an undergraduate in my group when ChatGPT hit, and I used to ask him, how much do you use ChatGPT? He said, 1,000 times a day. I said, 1,000 times a day? What are you using it for? He says, man, just chat with it like my friend, right? Right? So like, I don't know if that's a good use, if there's an environmental cost associated with that, right? So I leave it to you to judge. Okay. But more seriously, because I think we're all going to use a lot of it, like it or not, what are some serious suggestions? So serious suggestions. First, for providers, right? Select providers with real green operating practice, right? That means they're efficient in power use. You have to be a little bit careful. PUE is not actually a good measure, right? Carbon efficiency is a better measure. People try to get PUE, power use efficiency, but it's actually not quite right. You care about the carbon impact. You want to make sure they're connected to green power sources and grids. Notice I didn't say that they have long-term purchase contracts for renewable power. That's how they wash themselves, right? I said you want to make sure they're connected to green power sources and grids. So you want to know where it is and what power grid they're connected to, and then you can assess, actually, from public sources, how green that power grid is, right? Hopefully, you want them to be employing dry cooling or located in areas without water stress, right? Because water use is a concern. Okay, so that's sort of if you're selecting services or selecting providers for hosting or that kind of thing. For models, right? So what models to use? Well, use appropriate models. Okay, that's complicated. But just keep in mind, the biggest models aren't necessarily the most appropriate models. The cheapest models aren't necessarily the most appropriate models, right? Appropriate models from an environmental point of view would be things that are the right size for the task, right? And maybe give you better performance on that task because they're focused and so on and so forth. So that may be a little bit more complicated. It's not just like I get an AI solution and it solves all my problems, right? But maybe I get a solution for deep research. I get a solution for superficial undergraduate course support or something like that. Maybe there's different solutions you need to have that are more efficient and targeted to purpose. And then finally, time of use, right? So I talked about this variability and flexibility and so on, this idea that you not only want to be in the right place, but you want to use it at the right time. Well, I don't think you want to think about it from the point of view of I need to schedule my users to work at that time. Dump that job off on the providers, right? And they're well equipped to do this. So the way to think about this is you want to create flexibility in use. right? What does that mean? That means there's some kind of use that we would call user-facing or user-coupled, like a chatbot. You need a response. Maybe it can be 1 second. It can't be 2 hours, right? That's no good. That's not a chatbot anymore, right? But if you do things that like are analyzing, deep research, analyzing a large corpora, right? Doing something, constructive meta for your entire collection or something like that, organize those things as flexible offline tasks and then serve them up to your providers as saying, okay, this can run anytime in the next week or the next month or something like that. The good thing is they'll probably give you a discount. They'll probably give you a discount to do this, and then it can be scheduled in a way that's green or low cost or something like that. So thinking consciously about how you separate coupled use from batch use or decoupled asynchronous use, right, is important because that can exploit variable carbon emissions and power cost. Okay? So that would be my advice, trying to be constructive here in the face of, I think, undeniable growth in AI use that is coming, right? So AI power demand growth is explosive, driven by growing model complexity, increasing applications, and of course use, right? Just numerical count of users. And it's critical to choose what models, where they are run, to reduce carbon and water footprint. It's also critical to create load flexibility of the type I was just talking about, where possible to enable green execution of inference. That's a big deal. Like Facebook does a lot of stuff like overnight, batch, offline. You'd think of Facebook as the ultimate kind of interactive thing. No, they're building and training big models overnight, offline, when you're not hitting them quite so heavily, to do something intelligent the next day. So there's lots of places where it's surprising you can find asynchronous use. And then just a caution, there's lots of greenwashing, so vetting vendor claims of green power or greenness or green operation is crucial. As unfortunately, mainstream corporate practice, sometimes people get mad at me for saying this, but it's basically fraudulent, right? It's basically fraudulent. The notion that on a contract basis I can just trade off all my brown problems on you, right? Just because you signed, no, not because you signed, because I signed something that says I get to take all the green rights for this power, is simply fraudulent, right? But that's accepted corporate accounting practice for sustainability today. So one of the jobs of people like me is to advocate to change that. So that's what we're doing, yeah. Okay, thank you very much. I'd be happy to take any questions. Do you want to do it? Yeah, go ahead.
Yeah, this is up.
Hi, thank you very much.
And I'll leave some slides with all kinds of references and stuff if you guys are interested, yeah.
Could you recommend some small language models or tell us what language models you use?
I don't think I would be a good source of that recommendation. Part of the problem is it's changing very fast, right? And literally, it's the case that people are taking and downsizing models to make them more efficient. There's huge pressure in the industry to serve efficiently, right? So I'm not the right person to ask that question. Yeah, sorry.
I liked you said at one point sort of academics are supposed to lead the way, and I feel in this area, in a lot of ways, we haven't. It feels like almost the second that the big LLM models came out, people were like, well, we have to use them. They're out there. What are you going to do? And we need to incorporate them strongly in academics, and our students are using it, so we have to use it. And it felt, in this weird way to me, like there was just huge pressure to immediately begin using it, and it was very uncritical. And it was this kind of defeatist approach, and also this fear of being left behind. And I wonder...
But we're still in early innings.
We're still in early innings, but when you're talking about... But I wish we could push back more on the conversation and this tendency of just being like, we can't stop. I mean, I don't know, stopping, but like that it shouldn't be ridiculous. And I'm not saying you're literally saying ridiculous to say we should stop using it or we should slow down. But I wish as an academic culture, there could be more of that. And I was just curious if you're seeing, where you're seeing like academics being maybe more successful in being like, actually, we want to prioritize this for certain uses, but not everything. And how do we handle that?
Can you turn the on button? It just gets feedback.
Oh, sorry.
Sorry, this one? Did you want this one? So it's a great thought. I think actually in practical terms, we're hitting some of those thresholds because it costs real money, it costs power, it costs environmental impact. So you can't just use as much as you maybe would like to. So that's one of the things that's happening. The second thing is I think that there's growing awareness of the economic, environmental costs and so on. And I think that if you're I'm sorry, I don't know what institution you're at, but if you're at an academic institution, it's a good thing to engage the popular opinion of the students, right, in these debates, because they're very, very environmentally, I think, conscious, right? And I don't think you're going to, wind up with no consumption, but you will wind up with a more balanced kind of perspective. So I'm optimistic. I think it always happens this way, that size or most advanced was synonymous with best, right? And everyone wants to deliver the best. I think there'll be a more nuanced view, right, of what that is, an opportunity to do these things more efficiently and more effectively going forward. Yeah.
Over here. So just related to that question, how do we ensure that there's enough transparency and genuine data so that we have accountability from these organizations, so that we as consumers can make genuine consumer choice about what we're using? Because it seems like a lot of the data that we have available to make those choices might not necessarily actually be helping us make those choices genuinely. And related to that, you also talked about the sovereignty of AI. We know that there's a lot of demand from all governments around data sovereignty and being able to do things locally with the data, or at least within our kind of country boundaries. How do we reconcile that with the kind of global load balancing and the opportunities to make genuine savings in terms of carbon emissions globally?
So for the first question, I think the answer is demand the data and prefer the providers that provide it, right? The situation we have in the United States is different than the situation that there is in Europe, for example. In Europe, I think there's a broad popular and governmental consensus to demand this data from the providers. In the US, there isn't. And you could say, it's for obvious political reasons. I don't actually think it's ideological. I think it's about power and interest arbitration in the United States. And it turns out we have very large successful industry in these spaces that are exploiting this data and hiding their operational practice, right? And whatever the reason for it, Europe has much less of that kind of force. But, we have voices, and the most we can do is to actually vote with our voices and vote with our dollars, right, to favor those folks. I'm sorry, remind me of the second question again?
It was about the data sovereignty.
Oh, yeah, data sovereignty, I think that's a good theoretical academic question, right? Which is, can you get the full benefits? We write papers about this stuff, of shifting stuff to maybe you shift stuff to North Africa from Europe, right? Or to Scandinavia or something like that. Or in the US, you shift based on time of day to different parts, or you shift around the world. There's an old idea in computer science. It's called, what was it called? It was either chase the sun or follow the moon or something like that, and you shift your hosting around the world. Theoretically, it's possible. I don't know of anyone that actually does it. The point is of the diversity is that there's plenty of diversity even in smaller regions, like within Europe or within North America or maybe the Americas or something like that. And so there's lots to be gotten, right, by exploiting that kind of flexibility. So I'd say focus on that first, right? We've got a long ways to go. And eventually those sovereignty, the issues, will play into it. But I think they're not the primary blocking things right now.
Unfortunately, we are at time, so I would like to thank Dr. Chien again for a really illuminating talk.
Thank you.